Okie dokie. Let's go. Multiplying radicals. That's where we're starting. So write this down. We've talked about adding and subtracting. This one, some people like it better. Some people still get confused. Either way, at the end, we always have to go and simplify a radical. Just like with our fractions when we're simplifying, like if we had 5 over 10, we have to say it's 1 over 2 for this. So I'm going to give you guys a few things here to look at. I'm going to say, let's explore this. I'm going to write down some multiplications of radicals. So we're writing these guys down. Okay. What I want you to do first with these 3 multiplications of radicals, I want you to go in your calculator. I want you to get the decimal approximation for each and write them down, let's just say to 4 decimal places. Okay? It's not hard because your calculator will spit out all the decimals, but write them down to 4 decimal places. Okay? Okay, so what is the first one? Root 3 times root 5. If I ask that as a decimal approximation to say 4 decimal places, what is it? Say that again, sorry. 3.8731. Everybody get that? Okay, and then there could be more, but we just said round there. What is 2 root 6 times 5 root 2? Okay, 34.6410. Okay, and then the last guy, 3 root 5 times a root of 2. Can you say that again? 9.4868. Is he right? 9.4868. Now I want you to try this one right here. The cubed root of 6 multiplied by the square root of, we'll keep it easy, 2. So multiply that guy. You should all know your cube root button, if you're looking, is just under the math button in your calculator, and there's a cubed root in there if you haven't used it. Should have used it last year in grade 10. Go to the math button. So in the calculator, hit math, and under math, option 4 is your cubed root. So that'll bring that up on your screen when you go to do it. What's that decimal? 2.5697. Is that right? Roughly, if it rounds to 8, is that what you're thinking? Okay, so rounding, but I mean, you got it right in your calculator anyways. Okay, so I want you right now to look at these things because we talked about these are decimal approximations, all these things in red, because we've actually rounded these at the end. I want you to try to think of a way with the person next to you or just by yourself, think of a way that we could get these as exact values. Exact values meaning we'll probably still have it as a radical some way. So I want you to try some ways and try to see, is there a way that root 3 times root 5, I can write it as an exact value, but it would still equal this. So doing something with the radicands, doing something with the numbers out in front, try to think of some different ways that we can keep this being exact. Okay, so what did we come up with? What can we think we do? And I think, Andrew, you had said something. So what? Okay, so tell me this first one, and you're going off, but tell me what root 3 over root 3 times root 5, what do you think we can do? Root 15. Does root 15 still equal this? Did you test it? Can I simplify root 15? Nope, that's as much as it goes. What about this guy? 2 root 6 times 5 root 2. Okay, so 10 root 12, which 2 times 5 is 10, 6 times 2 is 12. Did that still equal 34 and change? Now, is this in reduced form? No. What can 12 break up into? 4 and 3, which, if we look at it, square root of 4 is 2 times by 10, so we get 20 root 3 is the same as this. So we could see these are now exact values. Down here, what would this one turn out to be? 3 root 10, because 3 times 1. Root 5 times root 2 is root 10. Can root 10 break up? Pardon? 2 and 5, like the root of 2 times root of 5, but does that help me at all? No, because neither one's a perfect square. So now we get down to here, and this is where Andrew was saying something. Everything works until we get to the end. And what did you say? Yeah, the indexes are the same. Did anybody test it? Did anybody say, well, maybe it's the cubed root of 12? What were you going to say, Arno? The cubed root of the square root of 12. Did that work? So he's throwing things out. Did that work? The cubed root of 12, is it the same as this? No. So really, this would be as simplified as this gets. Okay, because as Andrew pointed out, if the indexes are not the same, we can't do anything with it, just like adding and subtracting. Okay, so we did learn if we could just multiply those radicands and multiply those coefficients and simplify, we're good to go. So we always have to be able to write in pre-calculus things in general terms. So here's our kind of rules in general terms. In general, the root of A multiplied by the root of B should equal what? The root of A times B. And then something like this, M times the root of A multiplied by N times the root of B. If I had to talk in general terms with no numbers, what would this equal? Yeah, M times N times the root of AB. So all that's good. Now the other thing that you're going to always see, like this should make sense. Multiply the radicands, multiply the numbers out front. We're laughing. Simplify it, and away we go. Now in math, you're going to see that we add these sort of restrictions to it now to make sure that this statement's actually true. So what I put out the back here is we're allowed to multiply the root of A times the root of B and get the root of A times B if A is greater than or equal to 0 and B is greater than or equal to 0. Yeah, that's just commas. What does this mean? Yeah, A and B can't be negative. This does not make sense if A and B is negative because square root of a negative. We can't do it. Same thing down here. We'd have the same restriction. We'd be saying A has to be greater than or equal to 0. B has to be greater than or equal to 0. But what about M and N? Can M and N be negative? They can be whatever they want. So we don't have a restriction on that. Okay? So as long as this is true. Now these things out the back, these don't affect the rule themselves. They just have to be there for mathematically to make sense. And then to sort of build on what Andrew suggested, we could say to multiply radicals, we need the same indexes. If we don't have the same indexes, we can't be multiplying these or combining them at all. And the other thing that I had mentioned, after you multiply, you again, capital underline, need to simplify the product. The product just being the answer to multiplication. So again, like fractions, it's just some things are expected that you do. You have to simplify this down to the simplest mixed radical. So multiplying, is it easy? Yeah, fairly easy. The hard part, again, is just going to come from simplifying. So simplifying is the basis of everything we're going to be doing with operations on radicals. Okay, so we're going to flip into here, and I'm going to give you, let's say, 3 questions, and I want you to come up with the answers. And these should not be too big of a challenge. So root 3 times root 7, the root of 11 times the root of 14, and then 2 root 5 times 3 root 8. So 3 small multiplications. Give it a shot. All right, so let's look at some of these answers. Root 3 times the root of 7. what do we get? Root 21, can 21 be broken up into any perfect squares? No, so that's good. That's it. The next guy, root of 11 times the root of 14. The root of 154. Did anybody simplify it? Did anybody try to simplify it? Did it work? Nope, that is our smallest root in that case. So this guy, what would this turn out to be? 6 root of 40 to start. And then I'm getting a 12 root 10 because that's like root of 4 times the root of 10, which this whole thing equals 2. So 2 times 6, 12, root 10. Great, who got them all? Awesome. So now we have to take it a step further. Okay, and it's not any more difficult. I'm glad that we went over foiling today because this is basically what we're going to have to do in our next little section here is examples like this. And we're just going to say this is how the instruction might look if you come across it on a quiz or a test or just on worksheets. Multiply and simplify, which you should be able to see that it's multiplication just the way it's written. Simplification, you should know that's just something you have to do anyway. So the root of 7 multiplied by the root of 7 plus 27. So the 27 has no radical sign, it's just 27. This is just like the things we used to do just with x's and y's or numbers. This 7 just has to be distributed onto both those terms in there. So what is the root of 7 times the root of 7? The root of 49. We'll worry about simplifying after. So the root of 49. And then what's root 7 times 27? I heard a few things. Pardon? I don't want decimals ever anymore. 27 root 7. We always want exact values now. So this is good. We've multiplied it. We need to simplify it. What's the root of 49? You guys overthink this. Now that we work so much with radicals, you really overthink what the root of 49 is. It's simply 7. So this whole thing just turns to 7 plus 27 root 7. So now can I go ahead and add the 7 and the 27 because they're both numbers? Why not? Yeah, they're not like terms. This has a root 7. This guy doesn't. So if we go back to our toy analogy, I have 27 root 7 toys, and I just have 7 ones. Are they the same toy? No, I can't put it together. That's it. That's simplified. So try this one now by yourself. Root of 2 times the root of 81 plus the root of 2. Easy enough. Sure. Kevin's question was, can I simplify before I go into it? Sure you can. I know. I'll say it louder so everybody can hear you. Okay. All right, we're going to look at it, but one of the biggest things you should do, and it was the same thing when we worked with fractions back in junior high and the beginning of grade 10 and things, if you can simplify anything before you start doing the work, you should. So right here, what does the root of 81 equal? 9 plus root 2. It's not wrong if you don't, you'll just have bigger numbers to simplify in the end. So now if I look at it, this is what I got. We distribute this in. So 9 times the root of 2 is 9 root 2. And then root 2 times root 2 is the root of 4. And I'm already seeing some people jumping ahead, and that's great. They're saying, well, that's 9 root 2 plus 2. Difficult? If you can do this distribution just like we used to do with polynomials and everything, this is the same, except the problem now comes from actually trying to simplify. So we're going to take it again one step further. No, don't do it. Here we go. Same thing. It's going to say multiply and simplify, but this is what we got. 3 times the root of 5 minus 2 times the root of 5 plus 4 root 2. So what's different with this as opposed to the other examples we just were doing? Yeah, I've got a binomial times a binomial in essence, so that means I have to do FOIL or a double distribution here. So if I look, I take 3 root 5 times the root of 5, 3 root 25, and again we'll worry about simplifying once we're done. So 3 root 25. Then I take that 3 root 5 and multiply it by 4 root 2. What's that? 12 root 10. And then a negative 2 times a root of 5, negative 2 root 5, and a negative 2 times a 4 root 2. So we think, what's negative 2 times 4? Negative 8, and there's no other roots, so it's just root 2. So things now are a little better. However, we could see there are some simplifications that can happen, or at least one. Yeah, the root of 25 is simply 5. So this is 3 times 5, so I get a 15 plus the root of 10 is as far as it goes. The root of 5 is as far as it goes, and the root of 2 is as far as it goes. This would be my final answer because I can't group a root 10 with a root 5 or a root 2. That's it. So don't overthink it. It's just a double distribution. So now, one that you have to try, and there might be some simplification that has to be done in this guy. 5 root 7 minus root of 2 times 3 root 7 plus 9 root 2. So multiplying this, again, it's a binomial times a binomial. Try to see what's happening. All right, same kind of example as last time. We just have to do a double distribution and simplify, or FOIL if you want to call it that. 5 root 7 times 3 root 7. What's that? 15 root 49, which will simplify at the end. And then 5 root 7 times 9 root 2. 45 root 14. Negative root 2 times 3 root 7. Negative 3 root 14. And then negative 2 times 9 root 2. Negative 9 root 4. Which we can see there's some stuff we could simplify because the root of 4 is simply 2. So right here, this is 9 times 2. Over here, the root of 49 is 7. So this is 15 times 7. Now, you should be thinking, can I actually simplify the root of 14? The only thing 14 gets divided into is 1 and 14 or 2 and 7. Nothing's a perfect square. But can I combine 45 of them with negative 3 of them? And how much do I have? Positive 42 root 14s. What's 15 times 7? Pardon? 105 plus the 42 root 14 minus 18. No, it's not root 2 because right here the square root of 4 is 2, so the root is gone. Okay. Can I simplify anything else? Yeah, 2 constants. What's 105 minus 18? 87. So 87 plus 42 root 14 simplified. That's as far as it can go. Okay? Does it matter which order it's in? So 42 root 14 plus 87 or this way? Not at all. Okay, like A plus B is the same as B plus A. No difference. Yeah. The 42 root 14 came from a positive 45 minus a 3. Leaves me with that. Okay.